Okay, welcome everyone to the IAMP1 World Seminar, which is an online seminar that is run by the International Association of Mathematical Physics. Today we have the great pleasure to have a talk by Ivan Corwin, who's going to tell us about extreme diffusion. So please, Ivan, take it away.
Thank you very much. I should say I initially planned a different talk, but then I didn't finish the paper in time. So this is a talk I've given a few times. If you've seen it, I apologize. Um, Maybe the preface is that the full title is Extreme Diffusion, or Was Einstein Wrong About Diffusion? And usually when somebody claims that Einstein was wrong about anything, they're at least a little bit crazy. So the goal of this talk is to convince you that I'm not crazy. And instead to provide you with evidence that Einstein's theory of diffusion may break down when you consider the extreme behavior of many particle diffusions. That is, the behavior of particles that have gone the furthest and fastest out of a great many particles diffusing in a common environment. So in place of Einstein's theory, I want to offer a glimmer of a new theory of extreme diffusion and a new extreme diffusion coefficient that complements the classical Einstein diffusion coefficient. I'll also try to describe some of the mathematical underpinnings of this talk, of this work, and particularly related to the realms of integrable probability and stochastic partial differential equations. So structurally, the first half will be about physics, and the second half will be more about the math. Let me also just acknowledge my collaborators in this. They're pictured along the side: Guillaume Barracon, my brother Eric Corwin, Jacob Haas, Pierre Ledussal, Hindi Drillick, Sayan Das, and Shalin Parekh, the last three being graduate students of mine. So before jumping in with the theory, let me start by explaining to you, if you need it, why extremes matter in many particle diffusions. So this picture shows the rapid and manifold mutations of COVID-19. While most mutations had very minor effects, some variants, generally those that had the greatest leap in the number of mutations, measured here in the vertical direction over the horizontal direction of time, those that had the greatest mutations became more contagious and virulent. So as we saw time and time again, it was the extremes in the diffusion in the space of COVID mutations that really defined the trajectory of the pandemic. Now, there are, of course, many more examples where extremes, the particles that diffuse the fastest and reach a given location the first, control the behavior of a system. So here's an example in the nervous system. When you prick your finger, there's a signal that's propagated between nervous cells, and there are these gaps, and you have neurotransmitters, and you don't need all of them to make it across the gap. You just need a very, very small proportion to continue the signal along. In astrophysical diffusion of photons in supernova shockwaves, you have a very disordered shockwave, and it's the particles the photons that reach us, that go the furthest and reach us the fastest, that we're able to actually observe. More abstractly, the spread of ideas on the internet. It's not always the best ideas, but it's the ideas that really go the furthest that end up reaching us. And going just back to the pandemic, because that was a big thing. At least in the beginning, the spread of the pandemic was not by neighbor to neighbor contact. That was not what really created the massive fast spread. It was by people who got on buses or airplanes or went to super spreader events. So again, extremes in the space of this diffusion. Now, none of these systems are simple or idealized diffusions. However, still a fundamental understanding of extreme behavior in many particle diffusions should play an important role in modeling the nature of various types of systems. And also, and I'll make this point a little clearer as I go along, in interrogating the hidden environment in which such diffusion occurs. It's important to understand the scales we're working with here of many particle diffusions, and they really wildly vary from ecological to astrophysical scales. You should park yourself somewhere in the middle, 10 to the 30 or somewhere like that. And if you think about it, if you have a theory that works at describing the behavior of 99.9999999% of particles, if you have 10 to the 30 particles, that leaves still an immense number of unaccounted for particles that can really behave rather differently. And so we seek to understand these atypical behaviors and learn something from them. So at this point, I hope I've convinced you that extreme behavior in many particle diffusions is important. And now I want to convince you that Einstein's theory could fail at modeling extreme diffusion and instead offer the beginning of a new theory in its place. But first, let me briefly recall the origin and nature of Einstein's theory of diffusion. So almost 200 years ago, and actually Hal reminded me, it will be 200 years in 2028, September, Robert Brown observed the erratic motion of pollen, so depicted here, in water and recorded its statistical behavior. And he also studied what happened when you took the pollen and you toasted it, or you replaced it with shavings of rock or coal. The point being that pollen may be alive, but toasted pollen or rock or coal is inherently dead. And so he found, however, the same sort of erratic motion. And this convinced him that the motion was extrinsic. It was an effect of the environment acting on the pollen and not the pollen choosing to do something. It took about 100 years for Einstein and others to understand that there was a hidden environment of chaotic water molecules that was actually driving the erratic motion of the pollen through many, many collisions. And this led them eventually to postulate a simple random walk model, which produced predictions for the variance and distribution of particle displacement as a function of time. So Einstein's theory was very quickly validated by Perrin, winning him a Nobel Prize. However, even early on, it was already recognized that the model had some shortcomings. In particular, at short enough times, the model behavior of a real system should be more ballistic than diffusive, the scales on which you have interparticle collisions. I'm going to be pointing out a potential another shortcoming of the theory. So the Einstein model was really developed to study the motion of a single particle or a small number of tracer particles. Yet it's really widely applied to model systems where there are many, many particles diffusing together. Of course, it's too much to hope to mathematically or even numerically capture the simultaneous evolution of tracer particles and the entire background of water molecules in which they live. So the Einstein model completely forgets about the environment, and it simply postulates that each tracer particle behaves as an independent random walker, and that the only remnant of the environment is through a diffusion coefficient for these independent walkers. So here's an example of a continuum version of the model. It's given by a system of stochastic differential equations where the index I takes values in some finite set, 1 through n, and each of the BI's is an independent mathematical Brownian motion, named, of course, after him, with a specific diffusion coefficient, all the same. So here we just see 3 examples of independent Brownian motions. And of course, you see that this model really misses something about real systems, which is that when particles are near each other in space and time, they are near each other forcing, that the water molecules that they are around may have similar effects on them. So an alternative model, a so-called random walk and random environment model, treats the environment itself not trying to model the whole nature of it, but it treats it statistically. It treats it as a random field with short range correlations in both space and time that bias the motion of these independent random walkers. So here's one continuum example. So what's shown here, the colors represent the directions and strengths of a bias field, Xi, at a given time. It's very hard to see the arrows, but you should imagine there are little arrows pointing you in different directions and different intensities at different locations. And as I vary time, those arrows kind of rapidly vary themselves. Each particle, each xi, is drifted according to its location in space and time, what that field is, plus an intrinsic randomness, Brownian motion bi. So the effect of this is that if you look at the trace of a few particles, here are 3, and I should say this is not a simulation, this is me being lazy and just copying and slightly rotating a single picture, but I'll show you actual simulations in a moment. But the effect of this is that the particles may actually follow similar trajectories, at least for certain amounts of time, until they kind of go their separate way. You should really think of this as akin to leaves in a stream that stick together until they hit an eddy and one separates and never comes back. So for the rest of this talk, I'm not going to focus on these continuum models, though there is stuff to be said about them, but I'll rather focus on a class of discrete random walk and random environment models, and I'll mainly focus in one spatial dimension. Here I've shown you 2. though I will have a few things to say about 2 and 3 or higher dimensions. And we'll try to understand the behavior of extreme particles in all of these contexts. So here's the model or the type of model that I will mainly focus on. This is a discrete model that Guillaume Barraquand and myself began studying almost 10 years ago now. Space is measured in the horizontal direction and time is measured in the vertical direction. And we've basically coarse-grained space and time. Particles are represented by these little black dots, and they inhabit these discrete parcels in space and time. Each parcel is randomly colored according to a color on the spectrum of blue to red. So we start with n particles at the origin at time 0, and we let them evolve according to independent biased coin tosses, where the bias is determined by the color at the given site. So blue sites are biased to move particles to the left. The more blue, the more biased to the left. The coin that's being used there is more kind of weighted in one direction or the other. And red is, of course, to the right here. There's no political implications of these colors. Or maybe there is. But anyway, the choice of this is, of course, even if you have a very blue site, there is some possibility that the particle would move to the right. It's just highly likely that it will move to the left. So each time that you do this, you flip an independent coin. So the trajectories conditioned on the environment are independent, but of course they're coupled to the same environment. Our goal is to understand, as a function of the number of particles and the time scale, and of course the distribution of the biases or the nature of the microscopics of the model, what happens to the outliers. The environment here, at least for the moment, I'm going to choose according to a very simple class of distributions. Later on, I will generalize in many directions, but I want to focus very concretely and imagine that the biases are chosen according to a beta distribution. Okay, so the beta distribution depends on 2 parameters, alpha and beta. The density is written here. It's supported on the interval 0, 1. So you think of when your random variable is close to 0, it means that's the weighting of the coin. It's very likely to go, say, to the left or to the right. And if it's very close to 1, the opposite is true. So there are 3 things I want to point out. So when alpha and beta are equal, then the bias distribution is at least symmetric. So I'll mainly focus on that case here. If alpha and beta are equal to 1, then the biases are uniform. That's the case that's demonstrated in the picture. I just choose uniformly at each site on the spectrum of red to blue, and I put a color, IID. As alpha and beta tend to 0 or tend to 1, I transition between a highly partisan and a highly nonpartisan model. So when alpha and beta tend to 0, I actually get a delta mass with mass 1/2 at 0 and mass 1/2 at 1, which means that every site is either perfectly red or perfectly blue. This actually reduces to what's called the voter model, which says that at every site, all the particles just move either left or right according to some coin flip, and that's these delta masses. Of course, if I start all the particles together, nothing interesting happens. They just behave like a single random walker. If I have many particles coming from different sites, then they start to coalesce in interesting ways. On the opposite side, if alpha and beta tend to infinity, the density focuses around 1/2, which is to say 50-50 coins. So it just reduces to the model of n independent simple symmetric random walkers. So I'll think of the extreme of alpha and beta to infinity as what I'll call the Einstein model, independent simple symmetric random walks, and then anything else I'll refer to it as our work. So let's look at what happens here. Here are instances of the 2 models run with about 10,000 particles each. You see the trajectories of the well, you don't see the individual trajectories. You just see where the particles are at each time. So they start all together and then they start to spread out over time. Now, you can tell by my labeling which one is the Einstein model and which one is our model. But imagine if I removed the colors and I removed the labeling. Without that information, just by observing the trajectories, could you directly understand which model is which? That's kind of the fundamental question that I want to ask. So let me do that. Of course, I'm leaving still the label, so I haven't actually done it here. So I've removed I've removed the colors. You don't see the background environment, right? But now you just see the trajectories of the particles. So here you see a single particle highlighted in both sides, and you see the sort of density gradient of where particles are. So it turns out that you really can't tell much difference between the two sides. If you look at it and you really look closely, you see that in our model, it's a little bit more, there's a little bit more of kind of typical paths versus atypical paths. So it's a little coarser, but at a physical level, you really wouldn't be able to tell the difference, right? You know, if you zoom out or you kind of smooth things out a little bit, the densities of where particles lie in both models actually end up being exactly the same. They both evolve according to the exact same heat equation. And this is actually good news because for this random walk-in random environment model to be a reasonable model, you would hope that if you look at the trajectory of a single particle or the bulk, that it will behave the same as under the Einstein model, because Perrin, again, confirmed that the Einstein model is pretty accurate, experimentally. So, okay, so this is not the place to look. The bulk is not really going to determine the difference between the two types of environments, the Einstein model and the environment, which has space-time randomness. So perhaps instead we should look at the extremes, right? This is going back to the theme of the talk. So if we look at the extremes, so here I mean, if you look at a given time, you look at, say, the location of the leftmost particle, you can see that in both models, you can ask, when does the leftmost particle depart from the boundary, right? Particles either move left or right by one. Eventually, no particles will be at the maximal or minimal locations. They will have decided not to kind of only go left. It's a simple exercise in both cases to determine the behavior of this separation time. So in the Einstein model, you're just looking at basically at each epoch, half the particles move to the left. Slightly. It's of course a randomized binomial, but basically half. So you expect log base 2 of n times until no particles are left on the left boundary. And that's of course accurate. And you can compute the variance around that, and you see that in fact it's a very small variance. In fact, the variance stays of order 1 as n goes to infinity. So it's very clear where that cutoff location, where that separation occurs. In our model, it's different because at each time you basically take a uniform 0.1% of the particles and you move them to the left. So you're basically multiplying independent uniform random variables and asking until what point that product is roughly 1 over n, right? So that's more or less the time at which no particles will live if you start with n of them. And that you can study by just taking logs and using the CLT and the law of large numbers, and you find that separation occurs at log base e of n, so a considerably earlier time by a factor. And actually the variance of that is also proportional to log of n. So it's much more random, that location. So this is nice. It's a nice mathematical observation, but I would argue it's not physically very relevant, because in a real system, a real physical system, there's no lattice, there's no notation, there's no notion of when particles separate from the boundary of a cone of where they could be. This is just not a physically real idea. So what would be a more valuable thing to study is how random the outlier location is as a function of the number of particles and the time at which you're observing that. So what do I mean by this? What I mean is that there are 2 levels of randomness in our model and 1 in the Einstein model. So in our model, you have a random environment, and then you have the location of particles that were sampled given that environment. And when I say how random, I mean choose an environment, sample n particles in it, and then observe at time t the location of the leftmost particle. And now repeat that whole process many, many times. Choose a new environment, choose sample n particles in it, look at the location of that leftmost, and build up a histogram for that. Study its variance, study its distribution, and whatnot. Try to understand how that scales as a function of n and t. In the Einstein model, there's no randomness due to the environment, so the only randomness is due to sampling. And of course, this introduces a difference. Our model has more randomness, there's more variance because of this. So what we'd really like to understand is, how do these 2 effects, the randomness due to the environment and the randomness due to sampling, what is the interplay between them? And can we somehow use this to uncover an understanding of the environmental contribution to this randomness, to this variance, as opposed to the sampling variance? So that's what I want to show you here. This is a result of theoretical work and numerical work, and there's actually also experimental work that we're working on. I don't have anything to report at this moment. What we've shown is that extreme particles carry a lot of information about the hidden environment in which they're diffusing through a new power law and a new coefficient that we call the extreme diffusion coefficient. Okay? So the theoretical work that is presented here is coming from a sort of n to infinity limit. The number of particles that I'm looking at goes to infinity, and I study certain properties. I'll come back to that in the mathematical section. These are the dashed lines in the picture. And the solid lines that are not as regular as the dashed lines are from numerical simulations that confirm the asymptotic theory down to very realistic values of n. The number of particles on the order of like 10 to the, well, in this case, 10 to the 7 is what's being illustrated here. So these are not large numbers in many sense. So what is being shown here? So first of all, the axes. The horizontal axis is plotting time. So how long do I run my two models, the Einstein model and our model? And I'm rescaling that time by log n. This is a very natural scaling, as you saw, because nothing really happens interesting in the models before time proportional to log n. Right? That was the time at which the leftmost particle separates from the boundary. There's no variance prior to that time. The vertical axis is plotting the variances of the things that I will describe. The axes are log, so that power laws should be visible as lines, they're linear, and the slope should correspond to the power law exponents. Or sorry, the offset is the power law coefficient. So in the Einstein model, which is again in n independent simple symmetric random walks, if I look at the variance of the leftmost particle as a function of time, and I repeat the experiment many times, many samples, it's pretty easy through extreme value theory, very standard extreme value theory, to understand what happens. And what basically happens is that there is some initial turn-on period around, as I said, log base 2 of n, after which you establish basically a power law of slope 1 with a coefficient that entirely depends on the Einstein diffusion coefficient for those underlying simple symmetric random walks. So that's the, if I highlight this picture, the thing that's labeled Einstein is it's the variance due to sampling, which is all the variance that there is in the Einstein model. So there's this very simple power law that goes very deep in time. In our model, something different happens. So first of all, the turn on for our model, this is the red line here, which kind of follows. Okay, it's these red and blue and purple are the kind of different examples. But there's an earlier turn on as to when the randomness due to the environment kicks in. It has this effect that we saw that you separate from the bulk earlier. And then you have much more variance due to the combination of the environment's randomness and the sampling randomness. But then eventually the sampling randomness takes over and the curves merge. So this happens at a time which is of order roughly log n squared. So there's really three regimes in the presence of the space-time random environment. Nothing happens in the short time high density regime. Particles are packed together. There's no randomness in the location of the leftmost. The medium time, which is between time log n and log n squared, is where you really do feel the effect of the random environment, and you have a very different behavior. There's a different power law. And then the long time where things start to kind of merge and the variance due to sampling takes over. Now, this seems nice, but I actually would argue that this is not very useful either. Because on a physical system, the time scale between log n and log n squared, if you have 10 to the 30 particles, log n is like 90. Log n squared is like whatever, maybe two decades larger than that. So the most that you'll be able to ever observe for like a real system is like 1 or 2 decades. And so it's really hard. Like there is a different power law here. I'm not going to go much into it, but it's actually really hard to observe it. And so in many ways, I think that this region where things look different is a bit spurious. It's a bit of a ghost, and it will be very hard to observe that in a real experiment. So it almost feels like what I've said is that the difference between our models is not really significant, because the scale on which you can really start to observe power laws, which is this long time, low density regime, you're not going to observe a very different power law. But I want to argue that all is not lost here. Remember, the behavior of the random walk-in random environment model, the variance of the leftmost particle of the extreme, is driven by two terms, by the variance due to the environment and the variance due to sampling. And what our theoretical work has shown is that these two effects are independent of each other, or asymptotically independent. On the other hand, the Einstein model only has the variance due to sampling. And so what it stands to reason is that if you subtract off the variance due to sampling in the Einstein model from our model's total variance, you get left with the variance due to the environment. And what's demonstrated here, this blue line and the yellow line, is what happens when you do that subtraction. If you take the von Corwin model, you subtract off the Einstein variance, you actually see a power law that lasts indefinitely. And that holds down to very small. So here I've given you 10 to the 7. We did this for 10 to the 2. And you see the same power law arising. It's a power law that describes the variance due to the environment as seen by taking this difference. So here I think is where we really learn something. It's that by observing the difference between these two variances, we're able to actually get something about the environment, this different power law. And in fact, what we show, and what I'll explain mathematically a little later in the talk, is that, so the slope is universal. This 1/2 is universal. I'll explain it has to do with the Edwards-Wilkinson universality class. But the offset, the coefficient on this power law, is non-universal. It picks up something about the environment. What it actually picks up is the variance of the environment itself. So the Einstein diffusion coefficient picks up something about the environment, and this picks up a different quantity about the environment. And so the hope is that by studying these extreme particles and looking at these differences of variances, we'll be able to observe something new about the environment that you can't just look at 10 to the 30 water molecules and say, this is the variance due to the environment. You need to look at certain effects and how those play out. And so that's what is really coming out of this, is a beginning of an understanding of this. Now, of course, this is numerics. This is math. This has not been validated experimentally. And that's actually where we're taking things. So I want to very briefly describe, before I kind of come back and really give you the mathematical formulation of all of this, some perspective on experiments that are being developed right now in my brother's physics lab in the University of Oregon. And I should say, you should stop me at any point if you have questions. I hope I've been clear about things. I will come back and things will become mathematically better posed soon as well. So experimentally, we're looking at doing the first experiments to actually precisely measure the extreme statistics of real many particle diffusions. So to our knowledge, nobody has sat down and actually studied these extreme particles of large diffusive systems. There are two types of experiments. The first, I think, is actually better suited, or a model is better suited to describe it. The second has some other interesting effects. So one type of experiment involves colloids, or fluorescent dyes, that are diffusing in a fluid in a quasi one-dimensional capillary. And there you're able to vary the type of the fluid, the viscosity, the different properties of the fluid, temperature, the number of particles, the nature of particles, the length of the capillary, and various other quantities. You have a camera so you start with all the particles localized on one end, and then you have a camera on the other end that just passively measures the passage time of particles. There are some setups of this where you can also measure as a function of time where particles are. You can do that for smaller numbers with colloids, like 10 to the 12. If you want to get up fluorescent dyes, like 10 to the 14 or something like that, you need to have a much more passive system, and you need to control for the effect of heating due to the camera and things of that sort. But in any case, you observe first passage distributions, which is somehow a dual to the location, the variance of the location as a function of time. First passage variance is of a similar nature, and we have a theory there as well. But this has a very nice property of first being able to observe some real diffusive system, but also trying to understand things we haven't thought about theoretically, like how does temperature influence extreme diffusion? Is there a sort of role in the same way that classical diffusion theory has? How do we understand longer range correlations in the environment and interactions between particles and each other and with the environment? The models I've described, particles do not interact with each other, nor do they modify the environment. So trying to understand those effects become much more important when you start thinking about real systems. Here's the actual real system, by the way. So it has been built, but finding a graduate student to do all of this, there's a lot of work to be done still. And then, of course, it takes a long time. So you have a centrifuge. We multiplex, I think it's 12 of these little capillaries. When I first started thinking about this, I thought these were going to be big, but these are like 4 centimeters long. And they have still, 10 to the 12, 10 to the 14 particles. You centrifuge to put all the particles as far out to the right as possible, to the exterior as possible. And then it slowly rotates and you have your microscope observing the inside, and you can measure passage times in this way. So this is something that we're kind of working towards. We don't have anything to report at this point yet. The other set of experiments, actually, where there are some results already, have to do with photons in highly scattering media. I should say I don't think our models are actually the right ones to study this, but nevertheless, these are interesting questions. So you can study this in 1, 2, or 3 dimensions. You have a tube that has highly reflective interior. You shoot or you have a disk, or you have a sphere. You shoot a femtosecond laser, with a high blast of very concentrated photons into it, so that they start in one location, either the center, it could be here, or it could be the center, or it could be the center of the sphere. And then you have photodiodes on the exterior that are just observing passage time. Now, inside of this setup, you have some highly scattering material. It could be, glass beads. It could be something much more complicated. And so, of course, the environment is no longer quite as dynamic as you would imagine in the first experiment. I should say the first experiment involves, it takes an order of a few days for the particles to really diffuse. So the environment is diffusing much faster than the particles in the environment in this model. In the second model, the environment is much more static. Photons move very quickly compared to the environment. In any case, so there is work to be done in understanding both of these models and the relation to our theory.
Ivan, so
Yep.
what does your space-time randomness correspond in to the
Yeah.
in this case of your brother's experiment?
Well, in the first experiment,
Yes.
it's pretty clearly the fluid, right? So
Okay.
you would put it in some sort of fluid. The fluid has microscopic thermal fluctuations.
Okay.
So those fluctuations are what are dry, it's like the pollen in water.
Mm-hmm.
The second one, I agree, it's a bit more of a stretch, because you could have something where you have little scatterers suspended in water, or a critical opalescence, but photons move very quickly, right? And so I'm not sure that the environment actually decorrelates that quickly relative to the time scale in which the diffusion of photons occurs. So that's why I have some skepticism about the second one. It probably is more relevant to study a quenched, fixed in time environment. The only thing I would say is there is some sense, if you have a driven system, so if you shoot a photon in one direction, say in a 2-dimensional plane, then if it tends to move in one direction, you can think of that direction as a time direction. And then transversal to that is a space direction. And then you have kind of in the time direction, you have a resetting of the environment that occurs. So in 2-dimensional space-time, time quenched environments, if there's a driving direction, you can reduce it to a 1 + 1 dimensional environment in many ways.
Okay, so in the first experiment, you don't have to, sort of generate randomness artificially.
Natural.
Okay, it's natural randomness.
The second one is also natural. If you have, microscopic glass beads floating in water, they will be jiggling.
Okay, thank you.
I just want to flag before kind of moving into the math that there are several other key directions. I mentioned that actually first passage times, when does a particle pass a certain barrier, is actually more relevant for these experiments. These are the things we can observe. So we have developed the theory in that direction, but there's still more to be considered. Higher dimensions, of course, being very important, and then general spatiotemporal models of random biases as relevant, say, to this second set of experiments I just described. Here's the pipe dream, the sort of ultimate goal of this. And then I'll stop on the physics side. We really want to understand how internal fluctuations of an environment manifest themselves in the motion of many particle diffusions. So a really key, like in the experiment, I'd say in the first experiment, the key differential measurement that we will make that should be able to at least disprove the applicability of Einstein's theory to extreme diffusion is the following. We contrast pairs of particle media, so particle media pairs that have the same bulk behavior. So in other words, the same Einstein diffusion coefficient. So you look at your tables of Einstein diffusion coefficients and temperatures, and you just determine, for instance, I'm going to look at a Newtonian fluid, say water plus glycerin, versus a non-Newtonian fluid, a polymer melt. And that's what I'm going to put inside of my little capillary. And I'm going to feed it with the same types of colloids. So at the level of the Einstein diffusion coefficient, you can tune it to be the same. But now you look at the extremes and you ask, are the extremes, the statistics of the extremes, the same? If they're different, then it means the Einstein model is wrong. You can't treat each particle as an independent random walker. The extreme value statistics that you get from that are just wrong. And that shows that there's more to the model. Now, of course, what you'd like to do is you'd like to be able to do what I said, take the difference between the theory predicted by the Einstein diffusion coefficient, that Einstein line, subtract off the empirical, that from the empirical variance line, and get a power law. And if you can do that and you get the correct power law, you can build up a table of extreme diffusion coefficients. And these will contain more information. Now, I'd argue that actually, ultimately, what we want to do is we want to use this as a microscope to interrogate and differentiate between different materials, different fluids, different objects that are difficult to observe the internal dynamics of. You could imagine, far down the line, shining light through a breast and trying to see whether it's cancerous or not, but depending on the scattering behavior. And of course, people already do something like this, but the more that you understand about the effect of the internal dynamics, the environment, the better you have. There was a question from Shannon. Can you already see the difference in the large deviation rate function? Wouldn't that be easier? So that's a great question. And the answer is that no, that's probably not the best way to go about it, because large deviation rate functions are really non-universal. Like you could hope, okay, so if you imagine two mathematical systems, Brownian motion and simple symmetric random walk, that have the exact same Einstein diffusion coefficient, the exact same law of large numbers, central limit theorem, and you take n independent random walkers, they already have completely different large deviation rate functions. So that it wouldn't tell you whether you were coming from a random environment. It would just tell you that you didn't know which of those two models you were coming from. So to really understand the random environment, you need to study the fluctuations in the large deviation rate function, which kind of doesn't care what the rate function is itself. It cares about the sort of variance, the effect, the sort of second order effect due to the environment on that. So I'll come back to this when I kind of give the mathematical formulation. Okay, so I would say based on the first half of this talk, maybe I've gone over more than half, but you would think that we set out to develop this theory of extreme diffusion, but actually this is not the way it worked. So I work in an area of what we call integral probability, and this focuses on how certain algebraic structures, like symmetric functions, quantum groups, solutions to the Yang-Baxter equation, how these give rise to probabilistic systems and tools for their asymptotic analysis, and how that analysis reveals much more universal behavior, wide universality classes. It turns out that the model that I described, this data random walking random environment model, we discovered it in that context, and then we figured out a good story around it, and that's what has led us in this direction. So I'm going to spend the rest of the talk describing precise mathematical results related or behind the first part of the talk, and then relate maybe one or two techniques if I have time. So I want to back up now, forget about the physics. Let's talk a little bit about probability. What is the mathematics behind the analysis of the Einstein model, the classical model of n independent simple symmetric random walkers? Okay, so here I just write down a general form, with its alpha beta, but just think of alpha and beta as equal, in which case every particle has a 50-50 chance of going left or right. So you see the trace of a single particle here. And then, of course, what this represents is, as a function of time, where the distribution of the particles are. So they all start together, and then at some later time, they're pretty spread out. Now, there are three types of classical results in probability, and I'm sure you have seen them all. The law of large numbers, central limit theorem, and large deviation principle. The law of large numbers just says that if I track a single particle, the trajectory of that, and I look at its velocity, its empirical velocity, xt over t, that will converge asymptotic, almost sure in various senses, to a limit. And that limit will be given by the microscopic drift of a single particle. So alpha minus beta over alpha plus beta over, in the case where they're equal, just 0. So the asymptotic slope of a simple symmetric random walk is 0. The central limit theorem, of course, is a refinement. You subtract off that asymptotic velocity, and you see that their randomness survives on a scale of square root of t with a certain coefficient depending on the microscopic. So this is describing basically the histogram, the spread of these particles as time grows, how wide that is. Now, as Shannon indicated, there is also the large deviation principle, or the large deviation rate function. And this measures how likely, unlikely things are. So we know that a typical particle will go at velocity, alpha minus beta over alpha plus beta. And then what if I choose some velocity x that exceeds that? What's the probability that my particle exceeds that velocity? And of course, it's going to be small. So I take the logarithm, I divide by t. The large deviation principle proved by Kremer shows that this converges to minus I of x, where I of x is something called a rate function. T is called the speed. And this rate function, in the case of simple symmetric random walk, is pretty simple. It's given by this formula on the bottom, this entropy function involving logs. And in general, for kind of general jump distributions, IID jumps, it's given by the Legendre transform of the cumulant generating function. This is a very well understood thing. The point is it's very small. Now you might wonder why does anyone ever care about rate functions, large deviations, things that are very, very unlikely? And of course, from statistical physics, we're kind of used to knowing that they matter when you kind of have other forces at play. Also, when you look at lots and lots of particles, they matter, right? Just think, I always give this example. If every time I turn my car on, there's a 1 out of a million chance it explodes, I'm not super worried about that because I'm not going to turn it on a million times. But in a given day in the United States, maybe 100 million people turn their cars on. And so that'd be 100 deaths a day. So we want to understand unlikely events. And of course, in the context of independent random walkers, the behavior of the maximum is determined by understanding the tail behavior of a single particle. So if you want to know where the maximum of n particles lives, I should basically find where is this tail behavior, kind of like 1 over n, right? Because when it transitions, when it's around 1 over n, I have 1 minus 1 over n to the n. I get a number that's strictly between 0 and 1. That's where I should expect to see the maximum. So I'm looking at this sort of what I'll call the 1 over nth quantile here. Now, so it turns out that when I'm looking at these maximums, if I look at as time progresses, when time is of order log n, if I want to know where the maximum is, I should exactly be looking at the large deviation principle. I should basically be solving an inverse problem involving the rate function. That will tell me where I expect to see the maximal particle. As time progresses past log n, it gets longer and longer, I actually start moving more in the direction of moderate deviations and eventually to the central limit theorem. If I have a million particles and I run for a short time, I'm looking at the maximum, I'm looking at large deviations. If I run for a really, really long time, the particles have separated so much that the behavior of the maximum is more or less determined by just the central limit theorem with some modifications. So you already see in the Einstein model that understanding large deviations and then these moderate deviations really gives you the sort of behavior. This is where all these power law behaviors and the coefficient comes from. Now, what about our model? So just to set the model maybe more clearly, we have a collection of IID biases. These, I'll call them BTX. These are the colors. And they're chosen according to some common distribution supported on 0, 1. For instance, the uniform distribution 0, 1, that sets the colors in the picture. BTX gives you the probability that if you were at position x at time t, you move to the right. And 1 minus BTX gives you the complementary probability you move to the left. So these are the weights of the coins that you use at every location. And each of these, so if you condition on the environment, once you choose the B's, you have now a probability distribution on the trajectory of a path, which is given by the environment, given the environment B. And I'm going to think of these as these X T's as like a sample of a random walk path in that environment. And of course, I will sample many of these, and that's where I get the picture on the right. Now, what is remarkable, and I've kind of alluded to this already, is that by self-averaging of the environment, because the environment looks the same, kind of statistically in all different locations, if I sample an environment and then I sample a random walker in that environment, that random walker actually satisfies the same law of large numbers and the same central limit theorem as if I replaced the random environment by its average. So in other words, if I replaced all these colors by just white, 50-50 coin flips, and I look at the trajectory of a particle there, and I look now in the colored environment, and I look at the trajectory, the velocity asymptotically will be the same, and the trajectory itself under diffusive rescaling in both cases will converge to a Brownian motion. So this is remarkable, but not so surprising due to the self-averaging. What's also remarkable is that in the context of the random environment, there is a large deviation rate function as well. And it is deterministic, but it is extremely inexplicit. It is maybe characterized by some infinite dimensional inexplicit variational problem, but it's not something you can get your hands on. So what I mean by that is choose your environment, look at the tail probability that your random walker went too fast in that environment, take the log, divide by t, maybe put a minus sign, take t to infinity. For almost every choice of environment, you will converge to the same number, I of x. I of x is deterministic. The thing on the left-hand side, before you take the limit, is random because the environment was random. What is I of x is a complete mystery. Now, I also want to say that this kind of limit is a little too coarse in many ways. We know that large deviations are the thing that are going to matter for the behavior of the extremes. But this limit, even if we knew what I of x was, the randomness that was on the left-hand side before we took the limit, the effect of the environment, the fluctuations of this kind of tail probability due to the environment is lost in this limit. And that fluctuation is exactly the thing we care about. It's the thing that tells us something about the environment itself. So we need to understand this better. We want to understand what was lost in taking the limit and what that tells us about the behavior of extremes. So the first kind of step in understanding all of this came from the realization that Barakwan and I had that there was a special model, this beta RWRE model. Turns out to actually be very nice. And I'll describe the results and then I'll explain to you in what sense it's nice. So this is just a reminder of the environment. And here's the theorem. And this just shocked us when we got to this. I'm going to give you the simplest case, alpha beta equals 1, the uniform case. There is a similar result for general alpha and beta. The formulas are a little more complicated. They involve some digamma and trigamma functions. Here it's very simple. So choose this uniform environment and look at the tail probability for the rightmost or the leftmost particle. Okay, in other words, look at the probability that a single particle exceeds some velocity xt, where x is bigger than 1. Or sorry, bigger than 0. You expect it to have velocity 0. That converges, the sort of large deviation rate function, as we know, exists. But in the case of the beta environment, it is completely explicit. And in fact, it is remarkably simple. 1 minus the square root of 1x squared. It's simpler than the rate function for the simple symmetric random walk, which involves logarithms and is actually very hard to invert because of that. Not only is there a simple rate function, but if you look at the tail probability, this log bt, pb, so this is the given the environment b, what's the probability that your random walker that you sampled exceeded position xt, and you add in the sort of asymptotic behavior, that fluctuates on a scale of t to the 1/3 with an explicit coefficient involving the rate function, in fact, and as t goes to infinity, that converges. So in the sense of I repeat the experiment 1,000 times or 1,000,000 times, I build up a histogram for all different environments for sampling of the random walk in it and looking at the tail, well, really looking at the heat kernel, the sort of tail probability for the random walk. that converges, the histogram converges to the Tracy-Whittem GUE distribution coming from random matrix theory and from the study of the KPZ universality class. So this was a big surprise to us, that random walk in random environment and kind of KPZ were together. In retrospect, it makes sense, and there are ways to see that. But this was also very useful because it told us exactly what that randomness due to the environment looks like, at least in this large deviation scale. I want to give you a sense of what this tells us in terms of the picture I gave you earlier. So remember, I mentioned 3 regimes. There's the regime for time between log and log n and log n squared. That's the medium time regime. This is what is dictated by the theorem I just gave you. If you recall, the large deviations only play the role on timescales of log n. Once you go far past that, once you go to timescales of log n squared, you need to start to probe the moderate deviations, kind of the tail, but not so deep into the tail. So the power law that I somehow referred to, and I didn't actually give you, comes from the theorem I just gave you. It tells you the shape of this curve here. But like I said, actually, even though mathematically I love this result, physically I don't think it's the thing that matters that much. The thing that really matters is the long time regime. So I will tell you a little bit more about this. I'll tell you a little bit more about where this comes from because it's interesting. But I want to now turn to the long time regime, and that's actually where we get a real universal result, right? The result I just gave you here really restricted to the beta environment. I don't know what it is beyond that. It should be true. There should be something like it true, but I don't actually know, for instance, what this I of x is or what this sigma of x would be. And that actually matters a lot for the sort of fitting of the curve. On the other hand, if I move into the moderate deviation regime, I can say much, much more. So what's shown here is the plot of the variance due to the environment. So this is the thing where I just look at the location, the location of this 1 over nth quantile. It's basically, sorry, I should have said this. So in the context of our model, I can define the environmental contribution to the sort of randomness of the rightmost or the leftmost particle by saying that I'm going to look at the location x for which the tail probability is exactly or approximately 1 over n. When I know that the tail probability is about 1 over n, I expect that if I took n independent samples, that's roughly where the maximum will be for those n samples. Of course, there's the sort of randomness due to sampling around that, but that is like a centering term. So this is what I call the environment. This is what I will call m then t. This is the randomness due to the environment, or the environmental contribution to the randomness of the rightmost or leftmost particle. I guess rightmost in this way I've written it. So what I'm plotting here is the variance of that location. How much does it depend on choosing a new environment and kind of solving for that tail probability location, this 1 over nth quantile. I do this for 3 models. One was the beta environment one, just the uniform, that's the red curve. Another is when I choose the environment, so the distribution of my B's, my BTXs, to be according to a density that's this yellow curve. It's some, I don't know, it looks quadratic or some ugly looking curve, but it's chosen to have the same mean, a half, and the same variance as the uniform, which I think is like a third. Or sorry, 1/12, not a third. And the third is the blue curve. And this is, you see, there's a delta mass at a half. There's actually, it's hard to see, 2 delta masses at 0 and 1. So it's a model where some part of the time you have 50-50 coins, some part of the time you have, only heads, and sometimes you have only tails. All 3 of these distributions have the same mean and variance. And what you see is that they have very different behaviors in the medium time regime. This is consistent with the fact that the result I gave you before was not somehow universal, or at least the coefficients are not universal. But once you get to the long time regime, remarkably, all 3 curves coalesce. In other words, it's only the variance, it's only the mean and the variance of the environment that seem to impact the long time behavior. And that's what this theorem says in the context of the nearest random neighbor random walk. It says, if you fix a mean, let's say a half, you could do this for general, and you fix a variance, so 4 times the variance, call it sigma squared. Then if you look at the moderate deviation, so this is a statement in terms of the tail probability, I look at not the large deviations. That would be like looking at time LT and looking at location LT or something past that. Here I look at something like L to the 3/4. This ends up being a sort of crossover from the large deviations to the central limit regime. And then I have some even smaller scale where I'm varying my location at which I'm looking at the tail probability. In any case, as a function of x and t, this quantity, this random quantity, depending on the environment, converges as L goes to infinity to the solution to the multiplicative noise stochastic heat equation. And the coefficient of that only depends on the choice of sigma, the variance of the environment. So the point here, if you prefer the language of the KPZ equation, the log of the heat kernel converges to a solution to the KPZ equation with a coefficient that depends on, again, this sigma squared. So what this is saying is that there is a certain regime of times, and this is where this time log n squared kicks in, after which the variance of due to the environment, this nth term, the sort of centering, only depends on this sigma squared. And that's what gives the coefficient of this curve, and that's what gives the power law. So actually, once you start going past that time, it actually, there's a bit of an interesting inversion here. So as you move to closer to the central limit regime, it's like decreasing this value of this number t here. So actually moving closer to the central limit regime is like moving closer to the 0 time limit in the KPZ equation. In other words, the Edwards-Wilkinson universality class. So the coefficient is coming from the KPZ coefficient, and the long time behavior is actually coming from the Edwards-Wilkinson scaling exponents, which is 1/2 in the scaling that I've described. I want to just close this discussion about the kind of results by saying that you can do much more, and I'll just give you an example. So we can do this actually for completely general space-time random walk and random environment models where you have a sort of stochastic kernel that mixes rapidly enough in space and time. So here's just a subclass of examples. And there's some kind of abstract stuff about measures on the space of probability measure. Let me just give you a very, very concrete example. You can imagine what's written here. Imagine that instead of having at every location a color, right? The color really tells you kind of the probability that you go left or right. Imagine instead that at every space-time location, these blue boxes, I choose a distribution on arrows that leave that location. Maybe I choose, maybe I can have arrows that go either to -2, -1, 0, +1, or +2 from where I am. And I have a distribution by which I choose the weights of those arrows. So a simple example is I choose a Dirichlet distribution with some parameter alpha. So, I just kind of choose a way of distributing mass 1 over these 5 arrows. And I do that at each location in space and time. And so I get a picture where hopefully you can see there are all these faint red arrows. So some places have thicker red arrows and some places have very thin red arrows. Now the rules are that when a particle reaches a site, it chooses amongst the arrows proportionate to their width, to the amount of mass that they the weight that they have. And then each particle chooses in an IID manner. So of course, if there were only 2 arrows, you reduce back to the nearest neighbor model. But here you can have much more, many more arrows. And so the question is, if you allow for this kind of general non-nearest neighbor model, and you again start with lots of particles, say at the origin, and you run it, and you want to ask again where the rightmost or the leftmost particle is as a function of time. How does that behave? Now, I just want to flag one thing in this picture. What are these black arrows? The black arrows represent the mean of the red arrows. Right? So the red arrows are a distribution on, say, the numbers -2 through 2. The black area, so once I choose a sample of these red arrows, I can compute its mean. So, this location has a mean that is highly positive, and some locations have means that are pretty negative. Some locations are pretty flat. So it's kind of measuring the local drift due to the environment. And of course, you can ask kind of how wildly do these local drifts change? And so here's what our results show. So first of all, if you look at the variance of the maximum of n particles at time t, there are two independent contributions. There's the variance due to the environment. In other words, you look at the tail probability of the heat kernel, you look at the variance of that, and then there's the variance due to sampling and independent copies under that distribution. Now, the variance due to sampling is asymptotically given by exactly Einstein diffusion coefficient. What would happen if you replace each of these random walkers, this random environment, by just a diffusion, a Brownian motion with the diffusion coefficient of the averaged environment? This is the same as the story I was giving you before. So that's the formula. I didn't give it to you. It's for pi squared dt divided by 6 log n. That's what you get from extreme value statistics. Now, the variance depends, and this is the formula, it depends on a coefficient that we call lambda x, and multiplied by square root of 2 pi dt, so the same Einstein diffusion coefficient over 2. So this is the t to the 1/2 power law. And this lambda x, this is written in terms of the ratio of two things, dx, which we call the extreme diffusion coefficient, divided by d minus dx times a half. What is this extreme diffusion coefficient? It's the variance of the black line, of the black arrows. It's the variance of the drifts imposed by the environment. How wildly is the environment changing in terms of the drifts? Of course, the Einstein diffusion coefficient is also something you can read off of this. It's asking what is the average variance of these red lines. So these sort of two different ways of looking at the randomness of the red lines, they give you the two coefficients. And this is something that is completely universal to these models. And so you see that we really are observing some microscopic property of the environment, something that we can actually, a way to measure this hidden environment in a way that maybe one couldn't without knowing what the environment was. If you don't see the red arrows, how do you infer something about them? I'll mention that there's some other interesting things you can do here. You could imagine situations where the black arrows are always the same, right? What if you have an environment which is balanced? It could still be random, but you choose, a number, the probability you go to -2, and you replicate that to be the probability you go to +2. And the probability you go to -1, you replicate that to be the probability you go to +1, and then you just put the rest at 0. You will then always have the black arrow be constant. So then this extreme diffusion coefficient is 0. And actually what will happen then is that you go to a third moment. And you look basically for the lowest moment at which you can determine the randomness of the environment. And based on what that index of that lowest moment is, it actually determines a different scale, a different moderate deviation scale in which you get to the KPZ equation or the stochastic heat equation. So for models that have additional imposed symmetries, there are similar results, but they occur at different time scales, which I think is a very interesting kind of super universality phenomena.
Ivan, can I
Yep.
ask a naive question? So you have this first equation that says that the variance of something is the sum of two variances. Is this something we can easily understand, like the total variance?
Yeah. So basically,
Okay.
the way you should think about it is that when you have an environment, it
Yeah.
creates a heat kernel, right?
Mhm.
It creates a tail probability given that environment. You're basically solving a recursion relation.
Mhm.
And in the vicinity where the heat kernel is like 1/n, it just kind of looks
Yes.
the same. It doesn't matter where that is. The profile around that just kind of decays in a typical manner. So when you sample from that, the environment kind of forces that all your sampling is occurring in the vicinity of this 1/n. But then the way that you sample, it's basically like some sort of Gumbel type behavior. So you have this Gumbel fluctuation due to sampling in the vicinity of this random centering term. That's basically how it works.
Okay. And this, the first thing, variance environment Tn, doesn't it depend explicitly on n?
Yes. So
Yeah.
well, no, I guess,
Okay.
right?
Yeah. Here you don't have n,
No,
so
it doesn't.
no.
It in fact doesn't, right? So if we look at times which are of order, say log n or log n squared, then you kind of, if you start to scale, if you scale time by a log n, then you need to put in a log n type
Okay.
factor. But no, in fact, it doesn't.
Okay. And the second one does depend on n.
The
Okay.
SAM one does, and that's
Mhm.
why
Yes.
you eventually have
Yes.
that at some
Okay.
point the SAM takes over. Initially, one
Okay.
is bigger, later the other's
Mhm. Okay. That's why your new diffusion coefficient doesn't depend on n. Okay.
yeah.
I see.
So
Yeah.
at this point, okay, and then I just translate that into the KPZ noise. So at this point, of course I could stop. I think I've gone over. I've hit my time scale, but I would be happy to say a little bit about techniques if people are interested in staying on. I can say a few minutes if you want. People should feel free to leave though. Here's just an example. These are pictures showing the coalescence of all these things. So let me not harp on that. Let me say something about how both results are proved. So first of all, how do you get convergent? How do you prove this sort of general convergence of the to a stochastic heat equation? You know, from the random walk and random environment model. So first of all, I'm not going to exactly prove it. I'll prove something in that direction. So first, let's look at the stochastic heat equation. It's a well-known fact going back to the 80s, Kadar and Molchanov, that the stochastic heat equation admits a Feynman-Katz representation, and that you can use that to extract formulas for moments. So the Feynman-Katz representation just says that the heat equation is given by the expected value under a Brownian path measure, that a Brownian motion hits location x at time t, say started at 0, times this sort of, well, some carefully defined weight exponential of the integral through the space-time noise of that Brownian motion. So C is representing space-time noise here. So of course, making sense of this takes some work, and you know, people of sort of Bertini and Cancrini, for instance, spent quite a lot of time on that. But nevertheless, using this, you can extract moments. So if you look at the kth moment at time t at position x1 through xk of the stochastic heat equation, and you integrate, or so you substitute this Feynman-Katz representation for each term, now thinking of there as being a sort of k-fold product of independent Brownian motions b1 through bk, and then you interchange the expectation under the disorder and the expectation under these k-fold independent Brownian paths, you get a formula which looks nice. So you can take this inner disordered expectation, and you end up basically looking at moments of exponentials of Gaussians. And that produces for you a term which is proportional to the exponential of the pair local time of these independent Brownian motions. So in the end, you get this representation for the moments in terms of k independent Brownian motions rewarded in some exponential way by their paired local time, you know, collisions. Okay. Now, of course, you can work further. You can write down beta ansatz formulas. You can write down contour integral formulas. I don't need that for what I'm talking about. You can do it. So the thing that really matters is these pair local times. How much time does BI and BJ, being independent Brownian motions, spend together, and then so on. Now, what happens in the context of our random walk and random environment? What's the analog? So we could imagine that we have a sample of a random walk in a random environment given some environment. Let's call it C for the moment, just to stick with the same sort of notation. And I'm going to be interested in looking at what's the probability that my random walk, you know, a random walk hits position xi at time t. And I'm going to look at the product of these. So you should think of these as some sort of heat kernels, you know, kind of like the stochastic heat equation. I'm looking at a kth moment of that. So this is really playing the analogous role of this kth moment of the stochastic heat equation. Now, in the case of k equals 1, just the first moment, it's really easy. The noise somehow just immediately goes away, and you are able to write down the expression on the left-hand side in terms of just the expected, so I'm going to use this curly E as the average transition kernel. So what happens if I take these red things and I just look at an average of what the weights assigned to each of the 5 different location, you know, arrows are. So that's what I'll call the curly E. And I can now just compute the expected value that a particle under that measure is at position X. So this is analogous to the fact that the first moment of the stochastic heat equation, the noise goes away, you just have the solution to the heat equation, which is like a Gaussian version of this. When k equals 2, you need to replicate. So each of these terms, you substitute in an expression for, well, you have the probability that you have your random walk hitting position x1 and then a random walk hitting position x2. And you can represent each one of these as some independent random walker, right? You have a path that's kind of, and then another path, and you want to know the probability that they hit the same, or that they hit certain endpoints. Now, in the same way, because these transition probabilities depend on the environment, you're able to actually interchange the disordered expectation with the random walk expectations. And you're able to develop a formula for this. Now, this formula involves a more complicated two-particle interaction. So basically, when the particles, when these sort of sampled trajectories under the Feynman-Katz are apart, they just behave like the one particle averaged environment. But when they're together, there is some effect of the common environment. And so this E2 object is no longer just independent random walkers, but it's actually random walkers that have some additional factor when they're together. And so there's a way of rewriting that additional factor, basically absorbing that as an exponential tilt so that you now have independent random walkers, but with an exponential factor that depends on this paralocal time. And with a little bit of work, you can extract, say, for k equals 2, what the effect of this exponential paralocal time is. And this allows you to make the matching between the discrete and continuous version of this. Now, I'll just mention that there's one subtlety here, which I just want to highlight, because initially I didn't understand this, and I'm surprised I didn't. But so what I just described, maybe very briefly, basically says that on the discrete, for the discrete model, the problem reduces to just looking at two independent or k independent random walkers that when they touch each other, they get some sort of factor. It's not exactly the exponential of the local, but they get some sort of factor that depends, that only is active when they're together. And now I want to say that my random walkers converge to Brownian motions. The amount of time that they spend together should converge to the Brownian local time, so the whole picture should converge from the previous slide. Now, the subtlety here is that just because two random walkers converge to independent Brownian motions doesn't mean that their local times converge to the local time of two independent Brownian motions. Think, for example, if the two random walkers one starts at 0 and one starts at 1. And then they just go left or right. They live on different sublattices. They will never touch each other. So in fact, they have no local time at 0. And yet the limit will have the local time of Brownian motions. Now, was there a question? A slightly less degenerate version of this is when you consider something like a sticky Brownian motion. And this is actually much more relevant to what I'm describing. Or a sticky random walk. So imagine rather than having two random walkers, I look at the difference between the random walkers, right? So basically what I have is something that's doing a free random walk, except when it's at 0, maybe it gets some additional reward, or maybe it stays there with some positive probability. Depending on how that is tuned, you can end up with more local time. So if, let's say, the probability you stay put is p, you will still converge to a Brownian motion. It will not get stuck unless you tune p to 10 to 1 as you tune your scale diffusively. But nevertheless, the amount of local time at 0 will get dilated as a function of this p. And this definitely happens in this case. So actually there's some subtlety. Let me just kind of drop it out, which is that in understanding the convergence of local times, you need to look a little bit harder. So for Brownian local time, you have this nice thing called the Tanaka formula, which says that the absolute value of b is written in terms of the integral of the local time and then the integral of the sine dB. This is a martingale, this thing in green. And what's left here is the local time term that we're interested in. There is a discrete Tanaka formula for any random walk, which writes the absolute value of the difference of the two random walkers as a martingale. There's a unique decomposition into a martingale and something. Now you should think of this something as local time-ish. We have no choice what this term is. It just comes out of determining how to write a martingale here. we know that the difference of the Brownian of these two random walkers converges to this absolute Brownian motion. You know, okay, maybe with some coefficient. We know that the martingale needs to converge to a martingale, and in fact we're able to show that this needs to converge to this green thing, and that forces that the red thing converges to the local time. So the thing that actually converges to the Brownian local time is not the local time at zero of the difference of two random walkers, but it is rather this complicated weighted local time. There are these coefficients, kappa L times local times at difference being equal to L. And these kappa L's are a little bit complicated. They're written in terms of some sort of instantaneous expectation of the differences, that you can write them explicitly. And so what you're able to actually prove is convergence of this local-ish time to the local time. But from the perspective of our problem, we don't care about the local-ish time. We care about the local time at zero. So how do you get the local time at zero from the local-ish time? Well, you need to relate the amount of time that you spend at each location, not just zero. And that is going to be determined by understanding the stationary measure for this difference profile, the difference of two random walkers. So you're able to study, actually write down, is a sort of birth-death process in a sense. You're able to write down the kind of proportional amount of time that you spend in each distance from the particles being together. And by knowing that this converges to some invariant measure, you're able to relate this quantity to the local time at zero and then relate that. So it produces a coefficient. That coefficient is what ends up being the extreme diffusion coefficient. That's what produces this interesting coefficient. Of course, it produces a very complicated version, and there's a lot of processing to get it in the nice form that I showed you. So that's the guts behind this universality result. Of course, this proves it at the level of moments, and there's some more work to prove it at the level of distributions, and but anyway, the essence of it is here. If I have a moment, I want to explain one other idea, which is what happens. How do you get this? How do you get the results in the large deviation regime? Where does this Tracy-Whittem stuff come from? So far we've seen where the KPZ or the stochastic heat equation comes from and why we have a universal result there. But you have no idea at this point why we can do anything about the level of this, Tracy-Whittem distribution. Well, it's a different story, and it's an interesting one. So let me give you a bit of it. So first of all, just to step back one moment, how is it that we, in the symmetric, simple symmetric random walk, how would one go about proving these results, these Einstein, the law of large numbers, the central limit theorem, the extreme diffusion, or the large deviation rate function? So one way of doing that is through Fourier series, Fourier analysis. You write down a recursion relation basically for the tail probability. You say the tail probability, it's a heat kernel, it solves the heat equation. And then you solve that heat equation by Fourier series. And if you do that, you can write down expressions directly or indirectly in terms of contour integrals, a simple complex contour integral. Here's a version of that. This is a formula for basically using the residue theorem for the binomial coefficient n choose k. And when you do that, that's what you would get more or less if you try to solve this. This is a very simple formula. You just use the usual binomial coefficient and the residue theorem to pick it out. But it's also a nice theorem. For instance, if you want to get asymptotics for n choose n over 2, or really n choose, n times x, which is what you need for large deviations, you just write things in Laplace form, in the exponential form, and then you do a little bit of study of the behavior, and you can pretty easily extract all the results that you want. Okay, this is not going to work for kind of completely general models, or I'd say more complicated. I guess it does work for general models, IID. But anyway, what happens if you try to do the same thing in the context of the random environment? So you still have a recursion that says that the tail probability depends basically on the tail probability one time before at all the locations that feed into that site. And so you have a discrete stochastic heat equation. That's what I've written down here. It's also called a random averaging process in the literature sometimes. basically I look at the average of the two sites according to these B's prior to where I am, and that gives me a recursion relation, and I have the relation between the tail probability and the solution to that. But this is not a constant coefficient equation. It's not homogeneous. So I can't just use Fourier theory. But if I look at moments, I can. I can use some version of it. I can use beta ansatz. So if I look at the moments of the solution to this recursion relation, which anyway was kind of the thing that we were looking at before, I can actually just plug in the recursion relation, and I get a recursion relation for the moments. Right? I can express each one of these in terms of the previous time and average of the B's. And I see by just using the binomial expansion inside of here, I get an expansion that so here I'm assuming all of the n's, n1 through nk, are the same. So I get the same B, Bn and Bn minus 1. And I basically get a mixed moment of B and times a mixed moment of the previous Z's, or of the previous Z's, but they're independent. So I can take the expectation, I get some coefficient. So what I've learned is that these mixed moments satisfy a recursion relation. If all the n's are the same, I can express it in terms of kind of a mixture of n and n minus 1 at the previous time times some coefficient, which is explicit. If some of the n's are different, then I get the same sort of expression, but on clusters where the n's are the same. So for each cluster where ni equals ni plus 1 equals ni plus 2, so on, I have this sort of relationship. But then on different clusters, I have kind of a direct sum of these relations. The coefficients here happen to be nice because I have a beta distribution. But for general distributions, I would get general coefficients, and I could ask what happens. It turns out that these coefficients that you get in the beta distribution are really nice. And the reason that they're really nice is because of some completely different result, or a priori completely different result, which is called a non-commutative binomial theorem. So I'm going to give you this, and then I'll kind of wrap it up. The non-commutative binomial theorem tells you the following. Well, okay, let me first give you the result of how we get how do we solve this system. So the system that we're looking at, it basically looks like, so if all of the particles, all these n1 through nk are different, then the thing is factorizes. The sort of recurrence relation is very simple. When all the locations are far apart, there's no interaction, and the recurrence relation is dictated by this operator sans-serif L. But it turns out that, but of course, this is what the true evolution. So what I call this curly L, the true evolution is the thing that actually determines the recursion relation for this UTN. So the recurrence relations agree when I'm not near the boundary of the Weyl chamber. The Weyl chamber is where all of the coordinates are strictly ordered. But when I'm near the boundary of that then I need to impose some boundary conditions. And so the following result holds, that if I have a function that goes from zk to the complex that satisfies that these boundary terms, these bi plus 1 terms that look a little complicated, when I apply them to my function u and I look at the boundary when ni is equal to ni plus 1, if I get 0, then if I apply the free operator, this sans-serif L to u, it's the same as applying the true operator, this curly L to u. So it's basically a way of rewriting the true operator that gives you the recurrence relation in terms of a factorized expression subject to two-body boundary conditions. And these boundary conditions involve these sort of nearest neighbor shift operators. This is like the bread and butter of beta ansatz, and the way that it comes up, the way that this result is proved, is through this theorem here, this non-commutative binomial theorem, which says that if I have an associative algebra in two variables x and y that satisfy these mixed relations, so which really replicates the boundary condition you're seeing here, if I look at the kind of binomial coefficient, with some weightings, x plus y with these coefficients to the kth, x and y don't commute, and if I normal order it, I get coefficients. So I normal order it using these relations here. I get coefficients, and these coefficients were exactly the same as the coefficients in the recurrence relation coming from the beta RWRE. So it's this non-commutative binomial theorem with a particular representation of x and y that gives me the relation between the factorized and the unfactorized system. And once I have this, I can go, because I know how to solve for eigenvalues or eigenfunctions of the factorized system. I can impose boundary conditions by certain symmetrizations and writing down certain expressions in that spirit, and I can write formulas. And so ultimately, we're able to write down contour integral formulas in the spirit that are more complicated than the one I showed you in the Einstein case. These are k-fold contour integrals, complex contour integrals. Each one has a role. The boundary conditions enforced by a certain ratio, the solution to the free equation, and the initial condition. And this is the starting point for analysis for proving all of these results. Okay, so I've gone far over. So let me just skip here's putting this into a bigger context of quantum integral systems. But let me just close by saying that we had a physical goal of understanding extreme diffusion and a mathematical goal of explaining what's behind this understanding. And both have a lot of ways to go and a lot of directions to be probed, but I think we also have some interesting understanding at this point. Okay, thank you. Sorry for going over.
Thank you very much, Ivan. We are a bit over time, but if there are some urgent questions, please feel free to unmute yourself and just ask the question.
Feel free
or
to
we
email
can-
me later if you are tired and want to go to sleep, because I know this is an international audience.
Then maybe if I can ask,
Sure.
could you say after all a few words about this quantum integrable systems, connection to quantum integrable systems?
Yes, yeah, happily. So the the story that I described for the KPZ or stochastic heat equation, I stopped short of saying that this local time expression is actually a solution, another Feynman-Katz representation of a solution to the imaginary time attractive delta Bose gas. But that understanding goes back to Kadar. Of course, the solution to that by beta ansatz goes back to Lieb-Liniger. The approach that I described to solving the beta RWRE is also of a similar spirit. And in fact, all of these can be unified in the language of what we call stochastic vertex models. So the model here, KPZ equation, stochastic heat equation, beta RWRE, gets replaced by the transfer matrix for a stochastic representation of UQSL2's R matrix, UQSL2 hats R matrix. So by stochastic, I mean you want that the weights given the inputs, you want that the sum of the outputs sum to 1. Summing over all kind of outgoing vertices, you want the sum of the weights to be 1, and you want that none of the weights are negative. That's, for instance, a stochastic 6 vertex is an example, but you have higher spin representations of this. You also have higher rank models for which there are some stories to be told as well. The evolution equation for the moments in either of the two examples I gave you corresponds to what you would call Markov duality. So Markov duality says that there are certain certain expectations of the evolution of these transfer matrices, basically of the weights, which solve themselves evolution equations. So if you look in the context of these stochastic vertex models, you have a Q parameter, a quantum deformation parameter. If you look at something like Q to the number of arrows, so you start with some configuration of arrows that's kind of evolving. If you look at Q to the number of arrows that are passed a certain location on the line, and you look at that at different locations, those play the role of these like Z's. They play the role of these mixed moments. So if you look at the moments of that, those end up solving a dual evolution equation, which actually ends up being self-dual, because it solves the sort of k-particle version of these stochastic vertex models, with a spatial or temporal inversion. And then you can explicitly diagonalize and write in these contour integral formulas, and all of this generalizes to these what are called, the way I've written them, they're called spin Hall-Littlewood polynomials. But these are general solutions, beta ansatz eigenfunctions that diagonalize this class of models. And then, of course, in order to do anything, like in Fourier theory, you need to know how to decompose and recompose initial data with respect to these bases, and that requires the development of a Plancherel theory, and the completeness and orthogonality. And I'll just say, and I didn't emphasize this so much, I'm working on the line. Working on the line is much simpler than working in a periodic domain. In periodic domains, you have quantization of the spectrum for the eigenvalue, for the eigenfunctions and eigenvectors, and so it's much harder to prove results and to work with these expressions. Because we're dealing with stochastic models, we can define them a priori on the line, and we can do the spectral theory on the line, and it's actually much simpler. It's not totally simple, but it is a much nicer sort of behavior. And so there's a very analogous to standard Fourier theory. There's a completeness and orthogonality, and this is developed in these works I mentioned at the bottom.
All right, thank
Okay,
you.
thank you.
I think unless there are any extremely urgent questions, I think we're going to close the
Yes.
official part of the meeting. Thank you very much, Ivan. Thank you all for attending. I hope that you'll all join us again in 2 weeks on February 17th. We'll have a talk by David Gontier about Keller estimates for eigenvalue distributions in the gaps of Dirac operators. I hope to see you all then.
All right, thanks for sticking around.
Concludes the official part of the meeting. If there are now any questions, we can stop the recording, and if there are any questions that don't want to be recorded,